Hi, welcome to this e-lecture on virtual memory and DMA. Okay, so in this lecture slides, we're going to be going through first some motivation for the memory, okay, in terms of technology and software perspective. We're going to be looking at the memory hierarchy, and then we're going to be focusing on the virtual memory. Okay, so these first few slides are just to give us some overview on where we started and where we are going. Okay, so if you look back here, you can see in the past we used to have memory tubes or vacuum tubes, and then moving on to magnetic technologies and so on. Okay, and of course right now we are very advanced. We even have up to DDR4, okay, in terms of the memory technology, and there's so much more capacity, okay, that we can pack into a very small footprint. Okay, so the technology that we have has really improved dramatically over the past few years. Okay, and this is another picture of a chip, 128 gigabyte DRAM chip. Okay, so this is just to illustrate that how compact we have made memory chips to be. Okay, so in terms of DRAM, okay, the capacity is growing at a very fast rate. Okay, the amount of storage that we are able to squeeze in, okay, into the memory chips. Okay, the bandwidth is also growing. Okay, the bandwidth is basically how fast, okay, you're able to access the memory. Okay, but the bandwidth growth is not as fast, okay, as we want it to be. Okay, and so that itself gives us some issue. Okay, so you can see that the capacity is growing at a faster rate compared with the bandwidth. Okay, so the latency improvement is still not that there. Okay, so that brings us to this processor and DRAM performance gap. Okay, so as you can see here, the CPU performance is increasing at a very high rate, okay, compared to the memory performance. Okay, and that is an issue because you have a processor that is able to run very fast, okay, but you have a memory subsystem that is not able to process information as fast. Okay, so in the end, your CPU may waste a lot of clock cycles just waiting for memory to respond or to be updated and so on. Okay, so that is a gap that needs to be addressed. Okay, okay, so this is just a quick overview on the technologies. As you can see, two main types of memory technologies are there. One is SRAM, the other is DRAM. Okay, in terms of SRAM, it is very fast. Okay, it's very fast. This DRAM is a bit slower. Okay, so you can see you have like a SUV there compared to a sports car over there. But the advantage of DRAM is high density. Okay, that means you can pack a lot more memory cells into a smaller footprint. Okay, compared to SRAM, because it takes up more transistors, the density is lower. Okay, so again, it's a trade-off between the space and the speed. Okay, so that is the trade-off that you have when you're choosing between SRAM and DRAM. And of course, in terms of more large amounts of storage, we have our magnetic disk, okay, a hard disk, okay, that we most systems have. Okay, so if you were to compare, okay, the quality versus quantity relationship, okay, you can see that uh, the registers, okay, registers are basically the sort of registers you use, okay, in your assembly language programming. Okay, so if you take ARM for example, you have a whole bunch of registers, R0, R1 and so on. So all these are internal to the processor. So since they're internal to the processor, they are very limited in space. Okay, so the capacity is very little. Okay, but they are very fast. Okay, they're very fast because they are within the processor itself. Okay, so the access time is very good. Okay, cost wise is very high. Why we say is high is because it occupies space within the chip itself. Okay, so you are limited by how big your chip can be. Okay, so that is the limitation. So in that aspect, the cost is very high. SRAM and DRAM are of course very popularly used. SRAMs are of course very fast, okay, compared to DRAMs. Okay, but again, the difference is the capacity. Okay, so SRAMs usually you have lesser, okay, and DRAMs you have more. Okay, and in terms of cost, SRAMs cost more because physically you have a lot more transistors to hold. DRAMs are a lot cheaper. Okay, hard disk, of course, what we have is you can have huge amounts of memory, but the latency is very high. Right? It takes a lot of time to access this memory, and it's of course very low cost. Okay, if you look at all this together, what we ideally want is a memory that is very big, very fast, and at the same time very cheap. Okay, so this is of course an ideal memory. Okay, a big and fast memory. Okay, but of course that is currently not exactly what we have. Okay, so what we are going to do is we are going to try and use a mix of memory technologies. Okay, so that the small and fast memory is near the CPU, and the large and slow memory is further away from the CPU. Okay, so it looks something like this, where you have different levels of memory, starting with the hard disk, which is at the furthest away and the slowest. Okay, so in terms of size, it's very big, but it's very slow. And then you have your DRAM, okay, and then your SRAM. Okay, so SRAM you can have multiple levels, and finally your registers within the CPU. Okay, so what is the basic idea? The basic idea is you want to keep the data that is frequently and recently used, okay, in smaller but faster memory. Okay, so if I know that I'm going to access some information regularly, then what I do is I keep that data in memory that is closer to the CPU, which I can access very fast. Okay, whereas uh, if I'm in a situation where I cannot find that data or instruction in the fast memory, then I go out to the bigger and slower memory. Okay, so that is the basic idea, and it works because of this thing called the principle of locality. Okay, and the principle of locality basically says that program accesses only a small portion of the memory address within a small time interval. Okay, so in terms of locality, there is two types. One is temporal, okay, one is spatial. So what is temporal? That means in terms of time. Okay, in terms of time, if I am going to access a variable right now, okay, there's a high chance that I may access the another variable. Sorry, if I'm accessing a variable now, there's a high chance that I will access the same variable again within a short period of time. Okay, so that is temporal locality. Okay, so as you can see here, okay, so for example, in terms of data, I access this data at this time, at the same time, at this time, this instant. Okay, so this particular address, okay, is accessed again and again and again. Okay, so that is what you mean by temporal locality. At multiple time instances, I access the same data again and again. Okay, spatial locality is if I am referencing an item, nearby items will also tend to be referenced soon. Okay, so for example here, I access this address location, okay, or this sequence of address locations, and after that I again access the same sequence again of address locations and again. Okay, and this is quite typical because many of our code, much of our code actually has a lot of loops inside. Okay, so it is quite common to have this kind of a situation where you are accessing the same group of instructions again and again, okay, for a period of time before you go somewhere else. Okay, so this locality has can be applied for both instruction as well as for data. Okay, and basically from this what we see is we can abstract uh, this information into what we call a working set, okay, which is basically a set of locations accessed during a particular time slice. Okay, so you may have programs that span across a very large address range, but what is important is if you look at a particular snapshot, okay, so you look at a particular snapshot in time, okay, you will see that you fulfill this idea of uh, temporal as well as spatial locality. Okay, so what we want to do is we want to exploit this, okay, to see what we can do to make our system better. Okay, so what we want is what is visible to the programmer. Okay, so the programmer has sort of a view of where information is stored, okay, and he can or the programmer can sort of use this information to decide how the coding should be done. Okay, but at the same time you can also have a system where it is transparent to the programmer, okay, and the processor automatically assigns locations to fast or slow memory depending on usage patterns. Okay, so there's two types of approach to this. One is you get the programmer to sort of figure out exactly where should go what at different points of time, or you let it be transparent to the programmer. Okay, now in terms of how to make a slow main memory appear faster. Okay, so when you have a small but fast SRAM near the CPU, which is this, we call this memory a cache. Okay, what is a cache? A cache is basically a small amount of SRAM that is placed very close to the CPU, and in many modern processors we actually say that the cache can be in the same chip as the CPU. Okay, and what happens is when you are accessing the main memory, the DRAM, okay, you keep a subset of it in the cache. Okay, and this is of course transparent to the programmer because it is purely managed by the hardware. Okay, so again this works because of the locality principle. And the other thing is how to make small main memory appear big. Okay, that is virtual memory. Okay, so the small main memory is your DRAM. Okay, but you want it to appear big. Okay, so how do you do it? You can use the idea of virtual memory, which is what we are going to be doing. Okay, again these are all managed by the OS. Okay, so you do not need to worry about it. It's transparent to the programmer. Okay, so again this is just another slide to show the memory hierarchy in terms of the speed and the cost. Okay, so as you can see, from offline storage to hard disk and so on, as you go upwards your speed goes up. Okay, similarly as you go upwards the cost also goes up. Okay, and of course in terms of memory storage capability, it goes down. Okay, so this is very small compared to becoming larger and larger. Okay, this shows an example of how a memory system may be designed. Okay, so this is our CPU itself, which is executing the instruction. So within the CPU you have registers, and what you have is, like I said, from the main DRAM, okay, you may have a SRAM cache, and the cache itself can be split into two types of cache. Okay, one is a unified cache, and the other you can split it down to another subset, which is the instruction cache and data cache. Okay, so these are all ways in which you can design a system. And from the main memory you keep a subset from the hard disk. Okay, so that is the virtual memory part. This is the cache part. Okay, so again let's look back at the motivation. What we know is hard disks are very cheap. Okay, and hard disk is where you store the actual application, okay, your code. Okay, but what you want is we want to make a portion of the hard disk, okay, look like memory to the CPU. Okay, so when you say memory, is the DRAM memory. Okay, so when you execute code you need to extract the code to the DRAM and then execute from there. Okay, so what we are wanting to do is we want to make a portion of the hard disk look like memory to the CPU. So we're actually going to be copying data from the hard disk to the DRAM. Okay, so that is what we want. But since the DRAM is very small, okay, we only are able to copy over a small subset. Okay, so whatever the CPU is currently interested in, that is the only thing we copy from the hard disk to the main memory. Everything else stays on the disk. Okay, so the whole idea is as and when we need, we swap things around. Okay, so the virtual memory system that runs in the background basically continuously keeps track of all this memory accesses to know what to keep in the DRAM and whether I need to swap out something and bring in something new from the hard disk over to the DRAM. Okay, so let's look at how this whole thing works. Okay, so what is a process? A process is an instance of a running program. Okay, a process provides each program with two key abstraction. Okay, one is the independent control flow. Okay, and the second is the private virtual address space. Okay, when you create a process, that process behaves as if it owns the CPU by itself. Okay, just like for example, if you open up your laptop, okay, and you launch the browser, that browser will believe as if it owns the CPU to itself, and you can do whatever you want with the browser that you've opened. At the same time, it runs on its own private virtual address space. Okay, so it will get access from the main memory to use some subset and do whatever it needs to do to keep its process running. Okay, and how are we able to do this? Okay, basically in terms of the OS multitasking, we have learned about the scheduling. In terms of the address space, okay, in terms of address space, we are managing it through what we call a virtual memory system. Okay, so let's look back at this uh, uh, demarcation of how memory is actually used for the different parts of a code. So we have seen this in the previous lecture, where you have text segment, data segment, BSS, heap, and stack. Okay, so whenever you write a code, okay, every process that you are writing uh, your code for has actually all these subsections on how it will utilize memory. In terms of a program, what it does it refers to virtual memory addresses. Okay, so virtual memory addresses is just a conceptual memory that can be very, very big. Okay, so as you can see here, it can start from all zeros to all F, which can be a very, very big memory. Okay, and all of this is done, okay, when you compile the code. Okay, so the compiler will make sure that when you compile the code, all the processors will occupy this virtual address space. Okay, now what is the purpose of this virtual address space and how does it actually help us? Okay, so imagine that in my virtual address space I have 64 bits, okay, for my address bus. That will give me 16 exabytes of memory. Okay, but in my actual physical memory I have only a few gigabytes. Okay, so how do I squeeze so much of virtual address space onto a small amount of physical memory space? And another thing that we also need to worry about is, as we saw, whenever I write a process, each process has its own section of text, data, stack, heap, and so on. Okay, and I can have multiple processes running in the system. Okay, so I also need to figure out which of these processes go into which parts of the memory. Okay, so that is another thing I need to figure out. Next is, how do I protect any shared memory resources? Okay, so if both process I and J are trying to access this shared resource, how do I go about protecting it? Another thing is also, how do we ensure that when both process I and process J want to share this shared resource over here, how can we ensure that they are able to share it safely without corrupting the data in any way? Okay, so in order to solve all these problems, okay, so what are the four problems or challenges? We first need to fit a huge memory into a tiny physical memory. Okay, so this huge memory is the virtual memory, virtual space, address space, and this is the actual memory that you have. Okay, and we also need to manage the memory for multiple processes. Okay, like what I said, each process that you have has its own text segment, data, okay, heap, stack, and so on. Okay, so we need to manage this, and we also want to make sure that the processes do not override each other's memory and are also able to share the common parts of the memory across multiple processes. Okay, so one way we can do that is by what we call indirection. Okay, so instead of directly having a process, okay, accessing a memory, what we can do is the process, okay, can access a container, okay, that will then decide where it wants to point to. Okay, so as far as the process is concerned, it only knows this container, and this container will then be able to uh, decide which physical object it points to. Okay, so that is basically how we can achieve indirection. And how does it work with uh, virtual memory? Okay, so in terms of virtual memory space, as we saw, each process has its own virtual memory address space. Okay, and what we want to do is all of these virtual processes or virtual memory addresses will be mapped to a physical memory, which is only a single physical memory. Okay, now how do we go about doing it? So we first need to understand the address space that we have. The virtual address space is definitely much bigger than the physical address space. So n is always going to be greater than m. So what we have is, in the virtual address space, we have a very big address space, so 000 all the way to FFFF, all the way F, and we're going to map this, okay, into a smaller address space. Okay, so this is a smaller address space maybe, and what we want to understand is that each byte in physical main memory is only one physical address. Okay, so in the physical address, it is all fixed, in a sense that every byte in the physical main memory is actually tied to one physical address. Okay, but it could be a situation where multiple virtual addresses map to a single physical address. So I can have a situation where this address maps here and this address also maps here. Same thing, I can have this address mapping here and another address mapping here. Okay, so multiple virtual addresses may now map to a single physical address. Okay, so in a simple embedded microcontroller system, okay, what happens is, when I say that I want to access this word at address location 4, for example, okay, so for example, if I say I want to do a read, okay, of this 4 byte data, and I put out the address as 0x04, okay, then what will happen is the data at this 0x04, which is 4567, would be read out and sent to my CPU. That is how simple embedded systems work. But in a system with virtual addressing, what happens is, your processor does not give you the physical address, it gives you the virtual address. Okay, and this virtual address goes through a MMU. MMU stands for Memory Management Unit. Okay, and this Memory Management Unit, what does it do? It translates your virtual address into a physical address. Okay, and then it will know exactly where I should read from, and then take that data and send it back to the processor. Okay, so a virtual memory can be thought of as an array of 2 to the power n contiguous bytes stored on a disk. Okay, so this disk is basically referring to the hard disk. Okay, because the virtual memory is basically very big in space. Okay, and we can say that this virtual memory can now be partitioned into a number of blocks called pages. Okay, and these pages, okay, will then, okay, will be translated to what we call a cache in the DRAM. Okay, but not all the pages, only some of these pages. Okay, so what we are saying is, from the hard disk space, okay, we are going to be able to partition the entire hard disk, okay, into a number of blocks called pages. Okay, so each of this is a page. Okay, but this is a virtual page. So a virtual page can have a certain number of a certain size, certain number of bytes, and in the physical memory, you also have the same page size. Okay, so whatever page size here you have is the same page size over here, but only thing you have lesser pages. Okay, because this is your DRAM. This is your DRAM, which is used as a cache, a temporary storage space. So when I'm going to access this memory, I will prefer to read it from my DRAM rather than my actual hard disk. Okay, why? Because the hard disk is going to be very slow, okay, compared to my DRAM, which is going to be very fast. Okay, so that is the difference between the virtual pages, which are stored on disk, and the physical pages, which are stored in the DRAM. In terms of a virtual memory page, it can have 3 basic statuses. First one is unallocated, okay, where it means that the page, okay, is not being used by the process. Uncached means the page is being used by the process, but it is not yet cached in the DRAM. Cache means the page is being used and it is cached in the DRAM. So let's see what we mean by all of this. So over here, we can see a process, okay, and it's mapping from the virtual address space to the physical address space. Okay, and what you see now is that those addresses were in blue, which means that these address spaces actually belong to this particular process. Okay, Those in red means those addresses are not mapped to this particular process. Okay, so there's no mapping from the virtual address space to the physical address space for this particular process. Okay, now in terms of mapping, a virtual address space can be mapped either to physical memory or to the hard disk. Okay, so the virtual address space could be mapped to either one. Okay, either the physical memory or the hard disk. Now let's look at an example over here. So here I have 16 kilobytes of virtual address space. Okay, so 2 to the power of 14 will be 16 kilobyte, and 2 to the power of 12 would be 4 kilobyte. Okay, and you have a page size of 64 bytes. Okay, so let me draw it out over here. So over here I have a total of 16 kilobytes. So this is 16 kilobytes of virtual address space. Okay, and each page size is 64 bytes. Okay, so this is 64 bytes all the way. Okay, so in terms of pages, okay, how many virtual pages do I have? I have 16 kilobyte divided by 64, which is 256. Okay, and in terms of physical memory, I have 4 kilobyte. Okay, and the page size is also the same, 64, and so on. And so in terms of the number of pages, physical pages that I have, will be 4 kilobyte divided by 64. So what does that mean? That means the 256 pages that I have must be mapped to the 64 pages that I have over here, from the virtual space to the physical space. Okay, so how do I go about this mapping? Okay, so this is the mapping that I need to do. Okay, from this space I need to map it to this space. Okay, so to go about this mapping, what I need to do is to first look at the number of bits that I need, okay, to represent both the virtual address as well as the physical address. Okay, now for the page size, for 64 bytes, we know we require 6 bits. Okay, so if I look at the virtual, okay, so the virtual address as well as the physical address, okay, so both of them, the lower portion will be the actual byte offset within the page. Okay, the byte offset within the page. So in order to represent 64 bytes, I need 6 bits here. Okay, 6 bits here and 6 bits here. Okay, and so what does this 6 bits refer to? That means within a page. Okay, so when I look at one page alone, okay, one page, okay, I have a total of 64 bytes. Okay, 0, 1 all the way to 63. Okay, so the 6 bits here, okay, the last 6 bits of both the virtual address and physical address tells me exactly which byte I am referring to within the 64 bytes of a single page. Okay, and now the thing is, for the virtual address space, okay, we know that I have 256 different pages. Okay, 256 different pages. So for the 256 different pages, okay, what I need to do is I need to have 8 bits for that. So I need to add 8 bits over here to represent the 256 different pages that are there in my virtual address space. But for my physical address space, I have 4 kilobytes. Okay, so for the 4 kilobytes divided by 64, I have 64 pages. So for the 64 pages, I need 6 bits over here. So over here, I need 6 bits. Okay, so just to be clear, this portion over here is to represent the actual byte I'm talking about within a page. This upper section here is telling me which page. Okay, so which page am I referring to? Okay, that is the upper portion. The lower portion is which particular byte I'm referring to within a page. Okay, so that is the way we look at the bits for both the virtual address and the physical address. Okay, so this is what we saw in the earlier slide, where the lower 6 bits, okay, refer to the actual byte offset, okay, within the page, okay, and the upper bits refer to the page number, both in the virtual address space as well as in the physical address space. Okay, so how do we do the sort of a translation? Okay, so what we need is actually a page table. Okay, a page table is an array of page table entries that does the mapping, okay, from the virtual address space to the physical address space. Okay, so if I look at this virtual page here, okay, there are a total of 8 page table entries here. Okay, and for each of these page table entries, okay, you can see that it points, okay, to a physical memory, okay, or it can also point to the actual virtual memory on the disk, okay, which is the hard disk. Okay, so it can point to both of these locations. Now let's have a bit more understanding of this page table. There's one page table per process, okay, and page tables are also stored in the main memory, which is the DRAM. Okay, a page table should have one entry corresponding to each virtual page. Okay, so if I have 256 virtual pages, I need 256 page table entries. Okay, and each page table entry has a status. Okay, this status bit basically tells us if it is uncached or it is cached. Okay, if it is cached, then what does the page table entry contain? It contains the actual physical page number. Okay, so let's see how it works. Okay, so if I see here in this example, I have a 256 different page table entries. Okay, that means I have 256 pages in my virtual address space. Okay, and for each of these uh, virtual address spaces, I have a mapping to the physical page number. Okay, so the physical page number tells me exactly where I'm supposed to map to, or where this physical virtual address maps to in the physical space. Okay, and you can see that if it is already been cached, the valid bit here would have been set. Okay, so that means the data is already in the DRAM. When the valid bit is 0, that means it is uncached. So that is why it is still on the hard disk. Okay, in this case over here. Now let's look back at this example. Okay, so this is what we already have. We know we have 16 kilobyte virtual address space. Okay, 4 kilobyte physical address space, and a page size of 64 bytes. Okay, and what we already saw is we have 256 virtual pages, 64 physical pages. Okay, and we need a total of 6 bits for the byte offset within the page. Okay, now for the page table entry, okay, for the page table entry, what we said is we need to store the actual physical page address, okay, within the page table entry. Okay, so if I look back at the virtual address space over here, okay, what do you see? You see that the lower 6 bits are, in this example, the lower 6 bits which refer to the page offset are the same. Okay, so since they are the same, from the virtual address, I can also get the page offset. Okay, so what I need is from the virtual address page number, I need to be able to translate to the physical page number. Okay, so in this case, for each physical page number, I need 1, 2, 3, 4, 5, 6. I need 6 bits for the physical page number. Okay, so that is what is shown here. I need 6 bits for the physical page number, plus I need one more bit for the valid bit. Okay, so that is what is here. Okay, so this information here is actually pointing to the actual physical page number, correct? So if I need 6 bits to represent this page number, so I need total of 6 bits over here. Okay, but at the same time, I need one more bit to say whether it is valid or not. That means has it already been cached or not. Okay, so that is the one valid bit here. So total I need 7 bits, okay, for each page table entry. Okay, and how many page table entries do I have? I need one page table entry for every virtual address page. So since I have 256 virtual pages, I need 256 multiplied by 7, which is 1792 bits or 224 bytes for the entire page table. Okay, so this is the number of bytes I need for the entire page table in this particular system. Okay, so how do we go about the address translation? Okay, so as you can see, what I have is the virtual address. Okay, so this is what I have. From the virtual address, okay, I extract out the virtual page number, and this virtual page number points to one particular entry in the page table. So you have to remember that if I have 256 pages here, then I must also have 256 pages here, 256 lines over here. So each virtual page number will point to a particular entry in the page table. And what I need to do is, when I am accessing that data, I will check whether the valid bit is set. If the valid bit is set, then I extract out the physical page number and I combine it with the page offset. So the page offset is the same for virtual address and physical address. And when I combine it, I know the actual physical address that I need to get the data from. Okay, so of course, where is this page table actually in memory? That is held in another register called page table base register. Okay, so this register will hold the address for each process on where this page table is within the DRAM space. Okay, so basically, when you are using this virtual address space, two things can happen. Either you have a hit or a miss. Okay, so what is a hit? So in this case, the virtual address space, a virtual address that is given points to this particular entry in the page table. And you can see that the valid bit is set, which means that the data has already been cached. So the information given here is basically the actual physical address page, okay, location. So I directly map to the use that to combine with the page offset, okay, to get the actual physical memory to get the data that I'm interested in. Okay, so that is what you call a hit. That means the data that you want to access is already present in the page table. Okay, that means it has already been cached in your DRAM. Now, what about a page fault, okay, or a page miss? In this case, what will happen is you are trying to, your virtual address is pointing to a page table entry, but the valid bit is 0. Okay, so if the valid bit is 0 means the data is not cached, okay, in the DRAM. Okay, so it is still pointing to the memory in the disk, not to the memory in the DRAM. So what happens, okay, when a page fault occurs? Okay, so I need to do a few things. First, okay, so let's look at the situation here. The user tries to access a memory location. Okay, that portion of the user's memory is currently on disk, so it is not yet cached. Okay, not yet cached. So what happens is you have a page fault. Okay, so when you have a page fault, it will raise an exception. So this is an exception is similar to an interrupt. Okay, and again, since the whole virtual memory concept is handled by the OS, the OS page handler will then will be invoked, okay, to load this page from the disk to the physical memory. Okay, so the page that is currently in the hard disk now has been transferred to the physical memory, and then I need to modify the page table entry, okay, and then return to the fault instruction and then resume the instruction. Okay, so okay, let's look at an actual example to see step by step what's happening. So right now I am at virtual page number 3, okay, and it causes a page fault exception because it is currently not cached. That means it is not in DRAM, it is in the hard disk. So what will happen is the page fault causes an exception, and the OS page fault handler will select a victim to be evicted. Okay, so in your physical memory, your DRAM, you only have a limited amount of space. Okay, and in this example, all the pages in the physical memory, okay, are already occupied. Okay, so all of them are occupied, so it will select one of them to be evicted. Okay, so that policy on who is selected, that is another topic, but we are not going to go into the details. Okay, but for now we assume that it is choosing this virtual page 4, okay, to be evicted from the physical DRAM page. So what will happen? It will evict that page. So the virtual page 4 will now point back to this actual virtual memory on the disk, while the virtual page 3 is now mapped to the actual physical page in the DRAM. Okay, and the page table has also been updated to say that it is now valid. Okay, but now the entry for 4 is now marked as 0, which is uncached. So previously this was cached, okay, but now it is uncached. Okay, but 3 previously was uncached, now it has been cached. Okay, so that is the sequence that happens, okay, when you have a page fault. Of course, then you also need to restart the offending instruction. Okay, so the instruction that caused this entire page fault to happen will now be restarted, and this time when it points to this virtual memory line 3 in the page table, you will get a page hit because you have just cached it into the DRAM. Okay, so again, if you look back at earlier slides, why does this work? Because of locality. Okay, spatial locality and temporal locality. Okay, so because of these two principles of locality, where if I'm accessing a data, there's a high chance that data nearby will also be accessed, and similarly if I'm accessing a data, there's a high chance that in this current time slice I will access that data or those instructions again and again, okay, in the near future. So because of that principle of locality, it works. Okay, so how about virtual memory for managing multiple processes? So you can think of it as this way. So for each process you can have its own virtual memory address, okay, and each of these virtual addresses point again to the same physical space in DRAM. Okay, so as you can see, you can have different virtual addresses, okay, from different processors point to a same common, okay, page in the DRAM. Okay, so an example could be a read-only library code. Okay, so both the processors are depending on this library code for something, so they are pointing to a same space in the DRAM. Okay, so again, the main advantages of virtual memory is it solves the issue of memory allocation in physical memory. Okay, and it uses fixed page size allocation, which means that you can have internal fragmentation if you do not use the entire page. Okay, so like in the earlier example, we use 64 bytes for each page. Okay, so if you do not make use of the full 64 bytes, then it will cause internal fragmentation. Another thing is you do not require contiguous allocation in physical memory for a process. Okay, so if you saw here, you can see that a process can occupy pages that are discontinuous in actual physical memory. Okay, and that is fine. Okay, so that is good because of that you do not have any external fragmentation. Okay, and in terms of protection and sharing, what do you have? You have this example here. So you can see that in terms of sharing, okay, virtual pages in separate address spaces can map to the same physical page. For example, process physical page 6, okay, which is used by both virtual page 2 for process 1 and in virtual page 2 for process 2. Okay, in terms of protection, a process cannot access physical pages it does not have a mapping for. So for example, this process cannot access this physical page 2, and this process cannot access physical page 8. Okay, so because there is no mapping. So if there is no mapping for a process from one of its virtual addresses to a physical address, then it cannot access that physical address. Okay, another thing is most modern processors have more capabilities in their MMU, memory management unit, where they also they also have the ability to offer memory protection. Okay, so what is memory protection? Memory protection basically extends the MMU to not only say map a virtual address to a physical address. When you do a mapping,
you not, besides the valid bit, okay, you also have certain things. So for example, what are your, in what mode can you operate in? So for example, the ARM processor can operate in different modes. Okay, so you can operate in thread mode, handler mode, and so on. Correct. So in what particular mode you can operate in, and what can you do to the actual memory? Okay, in terms of can I write to it, can I read from it, can I execute code from this memory, and so on. So you may have different type of permissions, okay, for different uh, address spaces mapped to the various physical address spaces. Okay, so that is the extended feature of the MMU, where it also offers memory protection. Okay, so let's look at the address translation over here. So in this example, the processor sends a virtual address to the memory management unit. Okay, so this is the first step. And after that, what does the memory management unit do? It fetches the page table entry by accessing the page table stored in memory. So within the memory, okay, it needs to go and read. So as you know, the page table is also stored somewhere here. Okay, so somewhere here we have the page table. Okay, so in order for me to know what is the mapping, I need to first send this uh, virtual address, okay, over uh, virtual address mapping over to the uh, DRAM, okay, and then from there I know what is the physical address it maps to. Okay, and after I get the physical address, then I supply the physical address, and then I send the data back. Okay, so as you can see, there is 2 times I need to access the DRAM. Okay, why is that so? Because the actual table, so if I go back here, okay, this table over here, okay, that maps the uh, virtual memory to the physical memory, this table, okay, is actually inside the DRAM itself. Okay, so I need to first take the virtual address, know which index I'm pointing to, and then read this information, okay, on whether it's valid and what is the equivalent physical address from the DRAM, and then do another access with the actual address, okay, combined with the offset. Okay, so that is what is shown here. So first I get the page table entry. After that I combine with the byte offset, okay, or the page offset, and then I am able to generate the actual physical address that I need to read the data from. Okay, so in terms of a page fault, okay, what happens? Again, the same thing. Okay, in terms of a page fault, I again get the information from the cache. I can get the page table entry. When I get the page table entry, what do I know? I know the valid bit as well as the page number, the physical page number. Correct? Okay, so the valid bit, once the valid bit is 0, which is this case, the MMU will trigger a fault exception, which will cause the page fault handler to be invoked. And what will it do? It will come in to evict one of the pages, okay, and put in a new page. Okay, and it will update the page table entry in the DRAM. After it updates the page table entry in the DRAM, it will then return the operation back to the original process to restart the faulty instruction. Okay, so those are two scenarios for the page hit and page fault. Okay, when you look at what is happening, you can see that the translation actually sounds slow. Okay, why? Because each time you need to access the memory twice. Okay, first to get the page table entry, and then again one more time to get the actual memory. Okay, so each time, okay, because of the translation, you need to access the memory twice. So how can we or what can we do to make translation faster? Okay, so the solution to this is to add what is known as a TLB, a translation look aside buffer. So this is in effect another cache. Okay, so it's a small hardware cache inside the MMU. Okay, and it maps virtual page numbers to physical page numbers. Okay, but it contains page table entries for a small number of virtual pages only. Okay, so again, it works because of locality. Okay, so what we are doing is we are creating another small cache just to store this table and keeping it inside the MMU. Okay, so what is going to happen is this: we have the full table in DRAM. Okay, but the full table can be quite big. Okay, in this case 256 entries. So what you're going to do is we're going to just keep a small subset of it, within the MMU itself. Okay, so within the MMU itself, okay, what we're going to do is we're going to keep the mapping between a virtual page and the physical page. Okay, as you can see down here, virtual page 6 maps to physical page 2e, so that information is captured here, and virtual page 2 is mapped to physical page 23, and that information is captured here. Okay, so the on-chip TLB, or translation look-aside buffer, actually keeps a small subset of the actual, okay, translation table from the DRAM. Okay, so this allows you to again minimize a double access to the, or try to avoid a double access to the DRAM. Okay, if you are already able to have a match within the TLB. Okay, and again, it works because of the idea of locality. Okay, so because of locality, there's a high chance that this will work, okay, for a subset of time before again you need to do an update. Okay, so what happens with the TLB? Okay, when you have a TLB hit, okay, a TLB hit, okay, it eliminates the cost of memory access for the page table entry, because when I have a virtual address, this TLB itself will translate the virtual address to the actual physical table, actual page table entry, and the mapping from the virtual address to the physical address, okay, the physical address is already done inside here. So I can straight away put the physical address outside and get the data in. Okay, so I do not need to do a double access to the DRAM whenever I have a hit. Okay, now let's look at this example here. So in this case, what is happening is I have a translation with page table in the DRAM. So this is page table in the DRAM. So I'm given this virtual address, 32 bits, okay, out of which 12 bits are for the page offset, okay, and the remaining are for the page number for the virtual address. Same thing here, 12 bits for the page offset and the remaining for the physical page number. Okay, as what we saw, the virtual page number will point to a particular line in the page table entry, and in that page table entry, what we need to do is we need to check the valid bit. If the valid bit is set, I take the data, which is the actual physical page number, and pad it together with the page offset, and that gives me the actual physical page physical address that I need to get the data from. So that is the actual physical address. Okay, how about with the page table hit, or with the TLB hit? If I do the same translation with the TLB hit, what happens? Okay, so the virtual page number, okay, what does it do? It gives me the point to the TLB. This TLB is within the cache of the MMU. Okay, it's within the cache of the MMU. And what happens is, over here I have a mapping to the physical page number 6. So this 6, okay, already tells me exactly which page I need to access in the DRAM, and from there I can take the byte offset. Okay, so I do not need to go to the DRAM just to get the physical page number. This physical page number is already obtained here. Okay, so with that I can directly access the memory and go to the correct offset within the page. Okay, so that is the advantage, okay, of the TLB, translation look aside buffer. Okay, but what happens if I have a TLB miss? Okay, if I have a TLB miss, it incurs additional memory access. Okay, why? Because when I first put out the virtual address and I try to look at my TLB and I realize that the TLB there is miss, what happens is I need to take that address, put it onto my actual DRAM. From the DRAM, I go to the page table entry. Okay, from the page table entry, there I take it and update the TLB. Okay, and then I restart the instruction, and then I have a TLB hit, and then I'll be able to get the physical address, and then I get the data out. Okay, so putting it all together, basically this is what you have. So a CPU outputs a virtual address. Okay, if your translation look aside buffer gives you a hit, you can straight away get the memory, okay, that or the data that you want. If it's a miss, then you need to go to the actual main memory to get a update to the TLB. Okay, subsequently, if the page that you want, okay, is not in the DRAM, then there is another fault, segmentation fault, which will then cause the data from the hard disk drive to be updated to the main memory. Okay, so that is basically how your entire memory system works. Okay, and as we mentioned in the beginning, the entire virtual memory is managed by the OS. Okay, so you do not need to monitor it or worry about it. Okay, the OS actually takes care of it for us. Okay, direct memory access. Okay, direct memory access is the ability for a processor to move data between a peripheral, okay, and the CPU's memory without direct intervention of the CPU itself. Okay, and it's the fastest possible way of transferring data. Okay, because it requires no CPU overhead and it leaves the CPU free to do other useful work. Okay, and it helps to increase the data throughput. Now, let's look at how DMA actually works. During normal operation, you can think of bus switch 1 being closed and bus switch 2 and switch 3 being open. Okay, so of course these are just switches there to sort of give you the idea of what is happening. So you can see that if bus switch 1 is closed, that means it is functioning. That means the CPU is having access to the address bus, okay, as well as the data bus. Okay, and with access to the address and data bus, it can move data between the memory and the CPU, okay, using its own instructions. Okay, and that is basically what you have normally, okay, when the system is executing. But when a peripheral wishes to take part in an I/O transaction, it asserts the transfer request input of the DMA controller. Okay, so that is this. So the in the situation where, for example, a hard disk wants to move a large amount of memory, okay, what it can do is it can generate a transfer request to the DMA controller. And what happens after that? The DMA controller asserts the DMA request to request control of the bus from the CPU. Okay, so once the peripheral device says it wants a DMA transfer, the DMA controller receives that request and transfers that request over to the CPU. Okay, because the CPU is still holding on to the bus, correct? So it requests for a DMA transfer, okay, from the CPU. So when the CPU returns a DMA grant, okay, the DMA transfer can then take place. So sorry, once the CPU gives a DMA grant, okay, then the DMA transfer can take place, which means that you will enable the switches 2 and 3, okay, and grant DMA access to the peripheral device here. Okay, at this point of time, what is happening is the peripheral is able to communicate with the memory using the DMA. Once the DMA operation is completed, the DMA controller hands control back to the CPU. Okay, so over here, basically, once the DMA is in action, the CPU is no longer controlling the bus, but the DMA controller is now controlling the bus, which means that I can now directly transfer data, okay, between the peripheral device and the memory without having the CPU involved. Okay, so the CPU is now free. Okay, so that is where the whole advantage of the CPU of the DMA comes in. Okay, so in terms of request, you can see the sequence here. First, the peripheral device requests a data transfer. Then the data transfer request is sent to the DMA controller, which then sends a DMA request cycle to the CPU. Okay, and once the CPU grants it, the data transfer, the DMA controller acknowledges it and then allows the transfer of the device, transfer of the data between the peripheral and the memory. The DMA request did not be initiated by the peripheral alone. It is also possible for the processor to initiate it. Okay, so in this example, if there's a need for a DMA transfer between the memory and the peripheral, okay, the CPU can send a DMA request over to the DMA controller, and once it receives a DMA acknowledge, it will then free up the bus so the DMA controller can take charge of transferring the data between the memory and the peripheral device. Okay, many DMACs are able to handle several interfaces which require their registers to be duplicated. Okay, so each interface is referred to as a channel. Okay, so you can think of it as similar to, for example, the UART. Okay, so remember the UART serial transfer module that we studied. Okay, so the UART itself can have multiple channels to do data transfer concurrently. So similarly, okay, you can have multiple channels configured, okay, to do DMA transfer. Okay, and of course, when you have multiple channels, since you have only a single bus, you still need to take turns. Okay, but you can sort of use different channels already pre-configured for different types of data transfers. Okay, in terms of actual data transfer, you have two modes of operation. One is called burst mode, the other is called cycle stealing. In burst mode, what happens is the DMA controller seizes the system bus. Okay, so it takes full control of the system bus, okay, and allows the data transfer to be at the fastest possible rate. Okay, so the CPU is effectively halted in the burst mode because it cannot use any of its buses. Okay, so that is the burst mode of operation. The other one is what we call the cycle stealing mode. In cycle stealing mode, what happens is DMA operations are interleaved with the processor's normal memory access. Okay, so what happens is you have half a cycle or you have one cycle. So within that one cycle, half of that cycle is for the DMA, the other half is for CPU, and so on. Okay, so what happens is you are allowing interleaving of DMA and CPU operations to happen. So it does not totally halt the CPU, but it allows the DMA and the CPU to run concurrently. Okay, so again, all these are transparent to you. Okay, depending on whichever mode of operation you choose, the processor will operate in that particular mode. Okay, so basically, I know this has been a long set of lecture slides, but we have covered quite a lot of important aspects of virtual memory as well as DMA. Okay, and basically that wraps up the entire module. Okay, well done. Okay, and what I want to say is with this module, you have actually obtained extensive experience and knowledge, okay, in both embedded systems developments, okay, together with key RTOS concepts. Okay, and of course, if you are keen to be a TA for this module next semester, please apply and do let me know, okay, that you're applying. And we always appreciate your feedback, okay, to help us improve. So if there's anything that you want to feedback about, not only this module but also for CEG program in general, okay, because I'm also one of the uh, members sitting on the CEG committee. Okay, so if you wish to give us any feedback about the module or about the CEG program so far, please let us know. Okay, so thank you and good luck, okay, for the exams. Of course, this particular semester we're not having exams, so good luck with the mini project and the term paper. All right, thank you.